So today we're going to talk about reinforcement learning, which is a topic that I love. And I see here that there are some chats. Thank you. So in reinforcement learning is very different to other approaches that are in machine learning. Machine learning always goes with supervised learning when you have a data set and that data set is labeled. And we all know classification, regression, deep learning, random forest, all those things, concepts are related with supervised learning, and they have been exploded, and there are thousands of papers about them. Unsupervised learning is about clustering, and it's not so much developed because it's not so useful. But still, people know it. But reinforcement learning is a bit of a mystery. People hardly know what it is, and they speak very little about it. But this situation has changed in recent years, and we will see why. So if you see, our government in Ireland is testing coronavirus and is testing people because they want to have a feedback about their actions, and they want to know if their actions that they are taking are good or not. Well, in the same way, reinforcement learning learns from feedback. Okay, so there are two guys who influenced reinforcement learning very much. One is Richard Sutton. He's a professor from Alberta in Canada, University of Alberta. And he wrote a very famous book called Reinforcement Learning, an Introduction, and it has around 35,000 citations. And more focused, but also very important, more focused to industry is David Silver. And he led the project called AlphaGo, and we will talk about it in the next slide. But David Silver is also, he created a company based in London called DeepMind, who is very focused on reinforcement learning, and he optimized the servers of Google, the Google data centers. He saved thousands of millions by applying reinforcement learning. So if we see here, David Silver is here, Demis, which is his colleague. Demis is very smart as well. And Lisedo is a world champion in the game of Go. The game of Go has more, well, we will see a video that it explains it. So I wanted to show you this video, which shows very well what reinforcement learning is. And I want to, this presentation is only 20 minutes, so it's very difficult to resume or summarize what reinforcement learning is, but I just want you to know that it's very important, that it has a lot of potential, and it's really, really interesting. And I really have to say that from all the topics in machine learning that I came across, reinforcement learning is the one that I like the most. So here is a small video of 2 minutes, and I hope you enjoy it.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like CeADAR.
A match like no other is about to get underway in South Korea.
CeADAR is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge. The whole world is watching. Can CeADAR find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I didn't know something went wrong. Yeah, it's made him think. It's got to be a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Well, I hope you like the video.
Go.
I hope you like the video. I I really like. I get very excited every time I see it, and it gives me a high of dopamine. And reinforcement learning can be applied to a lot of domains. Generally, you can apply it to every domain in which you have to optimize a sequence of actions. For example, driving a helicopter, there is a sequence of actions you have to optimize. You can apply it there. Online games, of course. Managing different portfolios, of course. Controlling a power station or making a robot walking. That's another application. So if you're interested in reinforcement learning, which I hope you are, there are 4 free resources which I would recommend. Deep Lizard is a website that explains really, really well and in a nutshell what reinforcement learning is. David Silver has 10 lectures, 1 hour each in YouTube, and they are free. And if you like attending lectures, that's very useful. If you are a reader, go to the book. It's free. Reinforcement Learning and Introduction is the best book in reinforcement learning by far. And if you are more on the technical side, you can go to Jim OpenAI, where you will see that there is a lot of code applied to reinforcement learning, benchmarks, and so on. Now, as I said, reinforcement learning can be applied to a vast number of domains and applications. And here we go with the first riddle, which I like. You know that I like riddles. And if you know it, you can reply. What do you get when you cross a hamburger with a computer? And we're going to have 5 seconds. And this was a Big Mac is the answer. I know it's not very funny, but we have to keep going. As I said, I really like animals and I love them, and there are a few memes of animals onwards. Okay, there are some concepts in reinforcement learning that you have to take into account. One is the Markov decision processes. Markov was a Russian mathematician, and he created, Andrei Markov, he created all the mathematical support for reinforcement learning. Bellman was an American mathematician, and he created the Bellman equation. Temporal difference is a very important concept, and we will see why in the next slides. And also there is a trade-off between exploration and exploitation. And recently, deep learning algorithm methods or models were developed, and that catapulted reinforcement learning. Why? Because the Q table, which we will see, when the Q table started to grow exponentially, you cannot store it on a computer, but you can replace it with a deep learning model. And that's how deep learning helped reinforcement learning. Okay, here we have a Markov decision chain. We have the states, state 1, state 2, state 3, state 4. Those are the states, 1, 2, 3, 4, and 5. And those are the actions is if we move here, or we move here, or from 2 we move to 1, or we move to 3. Those are the possible actions. And the rewards is the value that you obtain. Here is this reward, this reward, this reward. Here we have a deterministic model. Why is deterministic? Because we always get the same reward in the same state. If this was, for example, 0.5 one time, and the next time is 1, and the second time was 7, and the fourth time was 0, then it can be defined as an stochastic process, which are much more difficult to model, but they are quite similar to the real world. Okay, So in reinforcement learning, we have to change our way of thinking. We have to articulate things and base everything on agent. There is an agent that takes actions, and those actions are taken on an environment. And the environment gives a new state. It takes the agent to a new state, and it gives a new reward. So the agent takes another action, and again, the environment is going to give it a reward, and it takes it to another state. So by defining the rewards, the agent will try to prioritize those actions that drive him to higher rewards and avoid those actions that drive him to penalizations or negative rewards. Markov decision process, this is the mathematical support for reinforcement learning. We have states, we have actions. If it is stochastic, we have the probability of going from one action to another state. That also can change. And also we have the rewards, which is in each state we get a rewards. What's the problem in reinforcement learning is that sometimes, for example, when we play chess, we only get rewards at the end of the game. So it's very difficult to figure out that the agent figures out which is the best action when the reward is just at the end of the episode. And to solve this, it is better to give the agent partial rewards. And we will know. And also very important is gamma, which is the discount factor, and it's explained in the Bellman equation that we will talk about. Okay, now here we have 1 minute, and it's good for me to rest a little bit. And we're 12 minutes, but see if you can find a C here. I can check here if the people are awake. If people are awake. Okay, chat, I couldn't find. Okay, so everyone. Okay, can anyone see the C here? Okay, well done, Andres. Can you see? Thank you, Andres. Thank you, Marisa. Thank you, Lauren, Richie, Tom. Okay, I see I'm not on my own. Thank God, I'm not on my own. You're following. Thank you. Okay, Lillian, well done. Okay, there was the C, okay? There was the C. So, well done for all you guys, and we keep moving. Now, the Markov decision process can be understood as the future is independent of the past if we know the present. So once you know, for example, a chess configuration, you have the board, you don't care who started moving, you don't care who, or once you have the money in the bank, you don't care about the previous transactions. All you need to know is the present, so you can take your next move and to know the future. This is one of the assumptions in a Markov decision process. Is we don't care about the past. All we analyze is the present moment. So in a Markov decision process or in reinforcement learning, we have to maximize the expect return. Okay, this is, imagine I am in a state 0. This is the reward I'm going to get in state 1, reward in state 2, reward in state 3, and so on and so forth until I get to the final state. So which is my goal? My goal is to make this number as big as possible, as high as possible. And this represents that all the rewards that I get from one state to the next. Okay, I'm going to mute all. Mute. Okay. Now, the problem is that it's not the same getting 1,000 euros today that getting 1,000 euros in a year. Which option will you prefer? Okay, you will prefer to get 1,000 euros today. Why? Because you don't know what's going to happen in the future. There is a certain uncertainty. And this is modeled by the discount factor. That is explaining the Bellman equation, and it's called gamma. So we're going to multiply future rewards by a factor called the discounted reward, by the discount return. So in such a way that the longer the reward is in time, the more discounted return is going to have. Okay, so reinforcement learning, this is one of the good things of reinforcement learning, is that it learns from the scratch. And one good example is how reinforcement learning learned to play Atari games. So there were like 20 different games. We give to the agent the input of pixels. The agent can play different actions, and it gets rewards from those actions. And just by the rewards that it obtained, the agent was able to play 20 different games at a multi-human level. Here we can say that here is the paper. It learned to play 20 different Atari games from the scratch. And that is very good because you can apply the same algorithms to different games, which is very good because you don't have to do tailor-made solutions that will take you a lot of time and a lot of resources. Okay. So here the problem was with Montezuma Revenge. In this game, the agent has to go down, go left, grab the key, go back. So to the moment the agent got a reward, it had to perform too many actions, and it never figured out how to play this game. So that is the problem. When rewards are at the end of very difficult actions, the agent finds it very difficult. So the solution will be give it a reward here, give it a reward here, give it a reward here. But for other games like this one, where it gets a reward immediately, it learns very quick how to learn the optimal actions. Okay, here is another visual challenge, and you have to find the dog here. There is a little dog here. It's slightly different from the panda. See if you can find it. See. Okay, I will give some clues. It's not here. It's from this line upwards. From this line upwards. See if someone. Andres, you're very quick today. You have been training. Marisa, well done. Okay. Okay, another one. Okay. Okay, Manu. Okay, there was it. The little dog was there, hiding. So very good. We move to the next slide, and I have to say that we are already in 19 minutes, so we'll finish soon. Okay, an agent has policy, which is the policy is a function that tells the agent in each state which one is the best action. And to see which is the best action in each state, we have to calculate the value function. And the value function is calculated with the Bellman equation and also the temporal difference. So the value function is how good a state is, okay? And once I know how good a state is, I will try to take the action that drives me to the best states. And as a state is good based on the rewards that it can get from that state onwards to the final state. Okay, so here is the Bellman equation. So the Bellman equation is like, it can be understood as recursivity, or at least I understand it like that. And it's like, from this state, I will calculate the reward that I get to the next state, plus all the rewards that I can get from the next state. And if I calculate that for all the possible, for all the possible actions, then my state's value is the maximum. In other words, we'll see it visually because with a formula it's more difficult. Imagine this is the state. I can take this action or this action. So I get a reward when I move to this state, and I get another reward when I get to this state, okay? Okay, but what's the value on this state? Well, the value of this state, I calculate it in the same way. The value that I can get, the reward that I get here, plus all the rewards that I get onwards. So it's like a recursivity. Once I know that, I go backwards until I get the value of this state. Now I have the value of this state and the value of this state and also this reward. So I take the one that maximizes this equation, and the value that maximizes that equation is the value of this state. And this can be applied for all the states. I know it's a bit difficult, but we will see it here. So the reward to get here is 1. So the reward here is 1. And here will also will be 1 because I get 0 rewards. Here I get 0 rewards, but I know that the reward here is 1. But here we are forgetting something. Why? Because the agent doesn't know if going to this stage or going to this stage, they both have the same value, which is 1. So which value should I pick? Well, I should pick the value that is closest, that is more close to the end, and I can calculate that by applying the discount return of the Bellman equation. And if I apply that, you will see that now this value is 1. This value is 0.9 multiplied by 1. This value is 0.9 multiplied by this value. Why? Because I am applying the discount factor. Now when the agent is here, which state will it pick? This one or this one? Well, it will go to that one. Great. Now, another riddle. Can you tell me what is the weight of the blue if I give you all these previous clues? Ta-ta-tan. Someone is applying equations. Okay, all we have to do is, I'm going to tell the solution. If we add this one, and this one, there will be 2 cats, 2 rabbits, and 2 dogs, okay? So if we divide that by 2, then we get the answer. Well, I know that I didn't give enough time to do it, but it's that we are running out of time. Okay, and we are almost finishing. One of the important concepts here is temporal difference, and temporal difference is very important because it calculates how good a state are as the difference between this state and this state. So the dynamic programming is very expensive computationally. Why? Because it has to explore all the states. Monte Carlo learning, it has to go to a terminal state. So the problem is that it can only be applied to those tasks that have terminal states. But temporal difference, in temporal difference, you can calculate one state, how good a state is as the difference between one state and the other. So if by moving to this state I get 3 points, if I move to this state I get 5 points, so I will pick the maximum difference, and that creates the option to apply it to problems that don't finish. For example, when you are trying to control a power station, well, the power station will finish if it explodes, but you don't want the power station to explode. So you can see how good a CeADAR is if you, for example, are able to create more energy or you're able to save energy. So the temporal difference opens a new horizon where reinforcement learning can be applied, and that is very useful. Temporal difference is a bit difficult to understand, but is one of the key formulas applied in reinforcement learning. Okay, so now we're going to skip this and this, and here is the formula, and here is the Q-learning algorithm, where new states of the Q table can be calculated by this formula. Okay, there is also a trade-off between exploration and exploitation, which is once the algorithm knows which is the best path, what should the algorithm do? So for example, if you know, okay, I know which is my favorite restaurants because I have been in all of them, but all of a sudden a new restaurant opens. So what should you do? Go to that restaurant or keep going to your favorite restaurant? So there is a trade-off there between exploration and exploitation. So even though we have our table that says this state is better, if there is a new state, maybe we should try to explore. So how reinforcement learning addresses this problem? Well, it has a formula that says that randomly, with a probability of 1%, of 2 or 2%, I will take a random action, and that is made with the objective of exploring new solutions. Okay, so imagine here. Here is the initial state, here is the final state. We have red squares, and the red squares are that we die, and the blue squares are frozen surfaces, okay? And in frozen surfaces, we can move through the frozen surfaces. So if the agent was here, where should the agent go? It can move to 3, it can move to 6, it can move to 8, it has different options. So we're going to generate a table, which is this table, and this table is called Q table. And if I was in state 2, it says going down is the best option you have, or going right is always. So the two best options are those two ones. But if I'm in option 15, it will say go to the right, which is 1, you get the higher reward. And if you're in 14, you never go left. Why? Because you will die. So, or in 14, never go left, you will die. So you better go right. This is the best move you can do. If you go here, you are getting away from the goal. So this is the Q table that the agent is going to use to learn its policy. And the policy is going to be always taking the best action, unless we go to exploration rate, which is taking a random action. Okay, the problem is, and now we finish, the problem is that for this small problem, the Q table is very small. But what happens when you are playing the game of Go? This table will go to terabytes and terabytes and terabytes of information. Or the same with chess, it goes to terabytes, terabytes, and terabytes. Or an online game, will go to terabytes, or petabytes, or whatever. So it goes almost to infinite. So what they do very intelligently was to replace that table with an artificial neural network, with a deep neural network. And by doing so, you can save a lot of memory. And that function, that model, is able to approximate this table. And that's what catapulted reinforcement learning to another level. So you have the Q-learning has this table, and with deep learning, you replace the Q-learning table with this. You have to train from time to time this deep Q-learning with the rewards that you obtain, so it can approximate even better. So, well, here is an example of the game playing Snake. Here it learns by itself, and you can see that the more episodes that it is trained, the more accurate and the best the snake is able to play. And here is an example of how Google DeepMind is the company that is in London. It learned to optimize the data centers of Google, and it saved 40%, which is millions of euros. Okay, so there is no time for more. And if anyone has any question, I will be very happy. So thank you for attending the conference, and that was it.